hosts who have a high security clearance, so that would be Alice and Simon, and you have hosts that have a low security clearance, that's Bob and Sam, and you want to make sure that packets that originated from Simon, data that originated from Simon, never reaches Bob. And the way we typically think of computer networks is what we call stateless networks are systems which have hosts, a finite set of host endpoints. They have switches which receive packets and then forward them on according to a static table. We have communication channels that usually are ordered and unbounded in typical model that you think about. And we have packets, and in this case we consider packet headers. So those would be tuples of a source, a destination, and some additional information like a packet type, which could represent the application that sent that packet or the protocol that it's running or stuff like that. But actually this model is a bit misleading. Actual networks aren't built like that. Actual networks have what's called middle boxes. And these are devices that are stateful, that reside within the network, and they're there to enhance the functionality of the network. So, for example, you would have a firewall for security, and you would have a cache server to enhance the performance of the network, and so on. And these devices usually dedicated hardware that implements some complex algorithm, or they could be general purpose servers that have some kind of network function installed on them. And as I said, they have state. And I'm sorry. So let me demonstrate how an addition of a middle box might cause a violation of the security property. So the same security property I mentioned before, we don't want any data from Simon ever reaching Bob. And so we have Alice who sends a request to Simon, and Alice is a high priority host as well, so she can see the response from Simon, and she indeed gets it, but the cache in the middle stores the response to that request, so that in the future you might want to optimize the network. But what happens when Bob sends the same request? So if, for example, in this network our security policy is implemented in the firewall or in the server itself, the cache bypasses that security policy and sends the response back to Bob. And we have a violation of safety. So we have data from Simon that reached Bob. So when we talk about safety in safety verification in networks, in the case of stateful networks, the problem is reducible to graph reachability. And there have been works that do that very well, and they scale to a large number of hosts. But once you introduce middle boxes to the picture, this makes everything somewhat harder. So the middle boxes themselves are complex software systems. They might have hundreds of thousands of lines of code. They may make changes to the packets traversing the network. So they may rewrite the headers, change some fields, and they're stateful. So they have, their behavior depends on the history of packets that they've seen. And in this case, we need to reason about that history. So if you consider the example I showed you a moment earlier, if the first thing that happened was Bob sending a request, we wouldn't have a violation in that specific history. The fact that we first saw a packet from Alice and the response was cached led to a violation of safety. So let's do a slightly deeper dive into one of those middle boxes. So this is a hole punching firewall. It's not exactly the same firewall we saw earlier in the earlier talk. Hole punching firewall allows packets from it separates our internal network and it protects it from the outside world. And it only allows packets from the internet into our internal network if it has seen a packet from inside going out at some point earlier. So it records, in a sense, a set of trusted hosts in the network. And initially, we have no trusted hosts. So if the host A sends a packet to the server, the firewall will drop that packet because it doesn't trust A, and then it doesn't do anything. If, however, the server sends a packet to A, the firewall will add A to the set of trusted hosts, and in the future, when A sends a packet, it will be forwarded onto the firewall, to the server inside. So that's the idea of like this is how a state and the firewall changes. And this example of this hole punching firewall, I'll refer back to it throughout the talk because it's simple enough to understand and clear enough to explain. So I do need to, there is a caveat here. So what do we do in this work? We don't try to prove the correctness of a middle box implementation. We don't go to the 500,000 lines of C code and try to prove that it indeed does what it claims it does. What we're interested in is proving the correctness of the network as a whole, the forwarding behaviors of packets going through the network. And for those purposes, we will use finite state models of the middle box code to prove the behavior of the network. So keeping that in mind, this is the full view of how we consider a network. So we have the hosts and channels and packets as before, and the channels are ordered and they're unbounded. And we have middle boxes, which are finite state transducers. So they accept a packet as an input, they may change state, and they might produce packets as an output or forward the packets out. And the safety property is also expressed as a middle box. So we have we add an error state to the middle box, and what we want to do is make sure that none of the middle boxes ever reaches an error state. So it's like an abort line in a piece of code or an assert false or something like that. And in this case, that's a middle box that expresses the property of isolation. So it goes to the error state whenever it sees a yellow packet arriving at host H3. So the property here is that H3 never sees yellow packets. Okay, and so okay. And this model is essentially equivalent to the model of communicating finite state machines. So these are finite state machines that can send messages to each other and have ordered unbounded channels, and that part is important. And communicating finite state machines in this model, proving verification for communicating finite state machines is undecidable. So we still want to do something, and to recover decidability, we introduce our first abstraction, which is unordered channels. And in this case, instead of having a sequence of packets, we have a multi-set of packets. So we remember for each kind of packet, the multiplicity of that packet on the channel. And this abstraction we've done in a previous work, and once you do that, you recover decidability, but with a relatively high complexity. This is exponentially space complete, proving safety verification in this kind of model. And not only is it a high theoretical complexity, but when we try to implement the algorithm that computes that, it also scales very poorly. It didn't really surprise us, but we did want to do something that scales better. So the next abstraction we introduced was the counter abstraction on the channel. So now instead of recording the multiplicity of each kind of packet on the channel, we only record whether a packet had ever arrived on that channel. So instead of multi-set, we represent channels as sets. And we go further and we apply a Cartesian abstraction to that. And we forget the correlations between the different middle boxes and the different channels, so the states of the different middle boxes and the communication channels. And once we do that, we have an algorithm or an abstract interpretation algorithm that is polynomial in the number of middle boxes, in the number of states in the middle boxes, the number of channels, and the number of packets in the system. So I said polynomial, but actually I'm hiding something here. The number of states in the system might be exponential in the number of hosts we have. So for example, the firewall, the same firewall we've seen before, this is the same model of firewall I've shown you earlier in a programming language that we designed for this work. And the way this programming language records the state is through relations. In this case, for the hole punching firewall, it has one unary relation recording the set of trusted hosts. And in order to record the set of, when you have a set as a state, you need to have a different state for every subset of that relation. And as it is a relation over the number of hosts, we are exponential in the number of hosts just by representation here. So what do we have here? So this is the same firewall we've seen before. It has the trusted relation to record the state, and it has two events. So this is an event representing a packet arriving from inside the network going out. And in this case, the middle box will add the destination of that packet to the set of trusted hosts and will forward it out. And the second event is a packet arriving from outside of from the internet, trying to get in. And if that packet, the source of that packet is trusted, then the firewall will forward it. If it isn't trusted, then it does nothing, essentially dropping the packet. And as I've said, the number of states to represent this firewall is exponential in the number of hosts. So this is kind of unfortunate, because we might have a lot of hosts in the network and we want to scale better on the number of hosts. So what we propose is applying another Cartesian abstraction. In this case, breaking down the state of the internal state of the middle box itself and ignore some of the correlations there. Which raises the question, how do you decompose the state of a thing into substates? And what we propose is what we call a packet state of the middle box. So this is an alternative representation of the state of the middle box. And instead of representing the state of the middle box as the contents of relations, we map each input to the middle box, so that each packet that might arrive at some point, to the set of, essentially the description of the execution. So in this case, the set of queries that hold true on that. I'll explain that in just a moment. The important part here is that it does depend on a few things that are specific to our work. So it lends itself naturally to reactive systems where you have an input arriving that triggers the execution of a program. It requires a finite input space, because otherwise you can't represent the entire state space in a finite manner. And we have a few restrictions on that the language places on the middle box design that makes this work. So what are those restrictions? As I said, this is, again, the same program, the same middle box implementation. The only way that a program can interact with the state is by having relation queries. So in this case, it can check whether the field source is in the trusted relation. Is source trusted? And in AMDL, this is the only way that you can query the state. You can't store previous packets that have arrived in local variables, and you can't iterate over the contents of a relation. You can only check if the fields are in some relation or another, and with the addition of maybe constants in the language, so that you could reference a specific host in the network, but not something that... So an execution is very strongly tied to the packet that has arrived now. And when we do that, this gives us the ability to represent the state as a mapping of the packet, of each of the packets in the system, to which queries that will be evaluated to true once that packet arrives. So in our case, when we have just the one query, is source entrusted? And when the program execution starts, all of the packets in the system are mapped to an empty set. Trusted is empty, we trust no one at this point, and no packet that will arrive will be evaluated true. And indeed, when a packet with the source 1 arrives on the external port from outside of our network, the query is not in the set, and the packet is dropped. It's not forwarded onward. So what happens when a packet arrives from inside our organization? We want to change the state of the system. So we want to add the destination of that packet. In this case, it's 1. That's the second field in the packet. We want to add it to the trusted relation. So we do that by adding the query for which it's true to the mapping from the packets that arrive from that host. And so far, this is just a different way to represent the state of a middle box. We haven't introduced another abstraction. It's isomorphic to the regular relations and tuples kind of way of looking at the program. But once we do that, that allows us another Cartesian abstraction that we can apply to this system. And in this case, we forget the correlations between the different packets and between the current state of the packet. So instead of storing for each packet which relations are in the set, we separate that for every packet. And this would be the abstract state after both packet types have arrived. So just as an example, if we want to concretize that state, this is what we get. We get a combination of each of the separate possible states of the middle box. So what have we had so far? We had the unordered and the counter and the network level Cartesian abstraction. And once we add the middle box level Cartesian abstraction, breaking apart the correlations between the packets, we are now polynomial in the number of middle boxes, packets, and channels as before, but we're no longer exponential in the number of hosts in the network. We're exponential in the number of queries in the largest middle box program in our network. And in general, there are way more hosts than the number of queries in the one program that is the largest program in our system. So this raises another question. When is this whole scheme precise, right? We've done a bunch of abstractions and Cartesian abstractions and broken apart a lot of things and a lot of correlations, and those correlations might be important. So we look at a specific class of middle boxes. We call them reverting middle boxes. And reverting middle boxes are middle boxes that may non-deterministically revert to their original state, the initial state with which they were started. So this is not unlike having a device on your network crash and then be booted up, clean slate. And presumably, network people take that into consideration, that eventuality. And how does that look in our same firewall example? So we have the states that represent the trusted relation, and we have the additional non-deterministic edges that go to the initial state of the middle box. And it turns out that if your network is correct when the packets can be reordered and the middle boxes may revert to their initial state, then our analysis is precise. So we don't add any false alarms to the verification. And this really depends on your point of view, but the idea of adding resets might seem to make things harder in some cases. So when you have Petri nets with the addition of reset arcs, this turns the reachability problem in Petri nets from decidable to undecidable. Whereas in our case, it really helps reduce the complexity of the verification problem. And we have some experimental results. So we've implemented this series of abstractions. We have a compiler that takes as input the middle box programs and the network topology and the initial configuration, and it produces a set of data log rules that are then fed into a data log solver, and the data log solver essentially performs the chaotic iterations and produces the least fixed point of the abstract system, and it gives us the final states in the packet space, and then we can check if one of those states is if one of the middle boxes is in an abort state. And we've done some tests, mainly focusing on how well this thing scales. And in our previous work, we could scale to a few dozen hosts in the network in smaller networks. So both hosts and the number of middle boxes. And here we've scaled to thousands of hosts, and takes it a while to finish computing, but it does the job. So this was one test checking the scalability when you increase the number of hosts in the network. This is another that checks the scalability when you increase the number of middle boxes in the network. So that's middle box instances. So the number of hosts was 1,000 here, and we added middle box chains in parallel to increase the number of middle boxes, and it also scaled quite well. And this is a good example of the fact that while we did add more middle boxes, we didn't add new types of middle boxes that had more queries. We just increased the size of the network, and we are a polynomial in that. So to summarize, we have a series of abstractions that allow us abstract interpretation in a scalable manner for computer networks. So that's the unordered abstraction and the counter abstraction, and two Cartesian abstractions, one of which is enabled by an alternative view of the middle box state, and it is precise for reverting networks with reverting middle boxes. Yeah. Thank you.
Questions? Okay, so you looked at, is it really on? So you looked at the scalability in the number of middle boxes and in a couple of other parameters. What about the unbounded case? Very often when you verify distributed systems, you try to prove it for an unbounded number of participants or...
So unbounded is a really interesting question. We thought it might help us, but it actually turns out that once you have an unbounded number of middle boxes, even an unbounded number of hosts, even when the number of middle boxes is bounded and the network topology is static, the problem is undecidable. That's a good question. We haven't implemented it and we haven't tried it experimentally. We stopped kind of at the theoretical point, but it could be interesting.
Use Petri nets, so those were used exactly for the unbounded case.
Yeah, that would be interesting to look at.
Maybe related to that question, so it seems like at least for the example, you're proving, you're looking at reachability problems, but at least for the examples that you gave, it seemed like the reachability sets that your targets, set of target states is upward closed, so you could actually look at coverability, and then some of these problems might still be undecidable even if you go to the unbounded case.
It's kind of might be a bit misleading because the reachability or the isolation problem in middle boxes is reducible to the coverability problem in Petri nets. So when we looked at the reduction to Petri nets, we actually used the coverability, and that's how we got decidable results and the complexity result, which is when you look at reachability, it's non-elementary. In that case, it was exponential basically. I'm sorry, I can't hear you.
I mean, reachability is undecidable, but coverability is still decidable in that case. So.
Any other? Yeah.
The undecidability of reachability with reset.
Yeah.
But what about coverability?
All right. On that note, thank you so much. And
thank you.
Break.